With this problem, we're actually going to use the math to do the gas laws, but we still need to go through some of the same processes. We still need to look at pressure, volume, number of moles, and temperature. The overall equation for this will be PV over NT equals PV over NT. One of those needs to remain constant. So not all four of them can be in the equation. It can be any one of those four, though. Volume and pressure units need to be consistent. So if you use millimeters of mercury for pressure initial, you will use millimeters of mercury for pressure final. Temperature must be in kelvins, and it's not usually given in kelvins. So when we look at this problem, which is problem number 626, and we will do part A, it says that a gas has a volume of 4.00 liters, and the units are important, at 0 degrees Celsius. They want to know the final temperature in Celsius, and N and P are not changed. We don't know what they are, but we know that they're not changed. Our new volume is going to be 100 liters. Now, let me note that in this case, both of these are liters, so we're in good shape. If we would have used 1,200 milliliters, we would have needed to make sure that both of our volume units were the same. Well, the first thing I'm going to have to do with this temperature is add 273 to it, which will give me 273 Kelvin. And since pressure and number of moles do not change, I will eliminate both of those from my problem, and I will have initial and final conditions. I'll have V over T equals V over T. So initially I have 4.00 over 273, and that is going to equal 100 over my temperature. Now to solve this problem, I need to have my unknown, which is temperature, in the numerator and isolated. Well, right now it's in the denominator, so I am going to multiply both sides times temperature. And when I do that, it effectively cancels temperature out on this side. So I would now have temperature times 4.00 divided by 273 equals 100. And now I need to get rid of both of those numbers. I need to isolate the T. So the 273 will get cross-multiplied up. We'll multiply both sides times 273, which will effectively eliminate it there. And we will divide both sides by 4.00, which will eliminate it on this side. So what I have when I'm left over here is T is equal to 100 times 273 divided by 4.00. So we're going to go from 4 liters up to 100 liters. This is a big temperature. We should have a big temperature change here. So T is going to be equal to 273.00 divided by 4. And when I plug that in, 273.00 divided by 4 equals, I get a temperature of 68.25. Now that temperature is in Kelvin. I will subtract 273 from that, and I get 65.52. Now that's a really, really big temperature, I know. But But those are the processes that you would need to go through. I picked a tougher one here because we ended up with the T in the denominator, which makes it a little tougher to work out. But that is my Celsius temperature. Notice I changed it into Kelvin, and then I had to change it back into Celsius to give them the answer. This is the type of problem that you can work out. Sometimes you actually have an additional P could have changed or N could have changed, but at least one of those needs to remain constant.